Hi everyone, this is Dr. S. Venkateswarlu, working a professor of EC at Institute of Aeronautical Engineering, Hyderabad. Today we are discussing about symmetric and antisymmetric FIR filter design aspects. Here, this is from that model. We'll try to cover. So from this, you have to follow this particular notation for designing a FIR filter. The notation is followed by capital letters denoted variables used in the continuous time signal, except for what you call the T. Where T is capital S, Fs, and F0, and what you call omega, omega S, and omega C. So lowercase letters denote variables used in the discrete time or sequence domain. So where F equal to F by Fs, F0 is equal to F0 by Fs, omega and omega. Square brackets denotes the sequences. Curved brackets denoted a function of the continuous variables. So where x of n and h of z. So using these brackets denote sequences, and curved brackets denote functions of continuous variable for designing what you call FIR filter using mathematical notation, mathematical expression. After writing the piece of code, we'll try to verify that output response. Okay, in cases where the domain is not clear, a subscript C will be used to denote a function in the continuous time domain, subscript of D for discrete time domain. Okay, for designing purpose, we require these all fundamentals, particular notations for designing that digital filter. Okay, that is SD of where it is assigned SD, where SD of Z equal to D power J omega, SC is equal to J omega. Okay, now coming to this finite impulse response direct and transpose forms. So we are not physically building the filters, but writing software to perform the filtering algorithms. This is the main motto for designing finite impulse response filter, like a digital filter. So, but if we were building the filters out of resistors, so adders and multipliers, okay, there are the design considerations which would lead us to choose one type of implementation over another. So both in hardware and the software. For building the filters like the FIR filter, digital filter, but writing the software to perform the following the algorithm. Okay, so there are two types of the implementations that in terms of the what you call practical aspects. Okay, this so least integrated square error design of finite impulse response filter. So let's SD of e power j omega denotes the desired frequency response. Since SD of e power j omega is a periodic function of omega with the period 2 pi, it can be expressed as a Fourier series. You know the term. So like this, you can identify the Fourier series. Okay, where SD e power j omega is equal to the summation n is equal to minus infinity to plus infinity. SD of n and to e power minus j omega n. So with this, so where SD of n, that SD of n is equal to 1 by 2 pi, 1 by 2 pi integral minus pi to plus pi SD of e j omega into e power j omega n d omega at an interval minus infinity less than or equal to n less than or equal to infinity. So like this is related to what we call the least integral squared error design of finite impulse response digital filter. Okay, here using this particular design of finite impulse response digital filter. So in general, SDE power j omega is piecewise constant with the sharp transitions between bands. Okay, in which case SD of n is of the infinite length and non-causal. Okay, so for this we have to find this design aspect. Before that, what type of objects are involved here, or that we try to find that finite duration where maybe in terms of where SD of n, okay, or in terms of this where HT of n with this, okay, of the length. The length may be in terms of this, what do you call 2m plus, what do you call 2m plus 1. Okay, who's the discrete Fourier transform STE power j omega approximates the desired discrete time Fourier transform SD d power j omega in some sense. This is the objective. Based on this objective, okay, so commonly used approximation criterion minimize the integral square error. Okay, for this case, it's 1 by 2 pi integral minus pi 2 plus pi. So mod ST of e power j omega minus SD of e power j omega square into d omega. For least integral square error design of finite impulse response filter, FIR filter, commonly use the approximation criterion. So we have to minimize that integral squared error. Okay, where so in this case where ST, that this one ST and d power j omega is equal to the summation where n is equal to minus m capital M to plus m ST of n and d power minus j omega n. Okay, so here in this case least integral squared error design of the FIR filter. So using the Parseval's relation, we can write in mathematical notation like pi is equal to summation minus infinity to plus infinity ST of n minus d of n square is equal to the summation where n is equal to minus m to plus m HT, where this ST of n minus SD of n square plus the summation n is equal to minus infinity to minus 1 H squared SD square of n plus the summation n is equal to m plus 1 to infinity SD square of n. Yeah, it follows from the above that psi is the minimum where ST of n is equal to SD of n for interval that minus capital M less than or equal to n, small n less than or equal to capital M. Best finite length approximation to ideal infinite length impulse response in the mean square sense is obtained by truncation. So it follows that all where using the Parseval's relation we can write in mathematical notation. After that we can use this pi is the minimum when ST of n is equal to ST of n for minus m less than or equal to n less than or equal to m. This is the best finite length approximations to ideal cases. Yeah, in infinite length impulse response in the mean square sense is obtained by truncation. Like this, we would like to observe this least integral square error design of the FIR distal filter. Okay, yeah, based on this, the causal FIR filter with an impulse response H of n can be derived from ST of n by delay. So where the delay is followed by H of n is equal to ST of n minus capital M. Okay, the causal or casual finite impulse response FIR filter H of n has the same magnitude response as ST of n, and its phase response as a linear phase shift of omega capital N radians with respect to that of ST of n. Okay, with this, try to design that what you call least integral square error design of FIR distal filter. Okay, now coming to the impulse response of the ideal filter. So, ideal low pass filter, it is we know that all response, expected response in terms of mathematical notation, that low pass filter H of n is equal to sine omega c n by pi n minus infinity to less than or equal to n less than or equal to infinity. It is the ideal high pass filter. Okay, so it allows only high frequency components. So we can consider this the ideal high pass filter. Okay, so like this low pass filter, it allows only low frequency components where h of L of n is equal to 1 minus omega c by pi, where n is equal to 0, minus sine omega c n by pi n, where n not equal to 0. So now, in terms of this ideal band pass filter, so previously we have seen that low pass filter and high pass filter. Now coming to that band pass filter. So within this, where the band pass filter is followed by HBP of n is equal to sine omega c2 of n by pi n. Here it is pi n. So minus sine omega c1 of n by pi n, where n not equal to 0. Where so omega c2 by pi minus omega c1 by pi, where that n is equal to 0. So like this, the ideal band pass filter is observed mathematically. Now coming to the ideal band stop filter. So like this, graphically we are right to verify that these mathematical expressions are involved for this case, and ideal multiband filter. So we can use the multiband filter with the mathematical and the graphical representation of this for designing a FIR filter. Okay. Now coming to ideal discrete time Hilbert transform. The transformer where st e power j omega is equal to j comma minus pi less than omega less than 0, where minus j 0, like this here, 0 less than omega less than pi, where that Hilbert transform st of n is equal to 0 for n even, 2 by pi n for n odd. Okay, like this ideal discrete time Hilbert transformer in mathematical notations are available. So with this, the ideal discrete time differentiator. So here HDIF, discrete time, discrete discrete time differentiator. Okay, so HDIF e power j omega is equal to j omega. Okay, 0 less than or equal to mod omega less than or equal to pi. So go on using this all value, consider this value. Now try to verify that ideal discrete time differentiator, where in SDIF of n is equal to 0, where n is equal to 0. Okay, if cos pi n by n, where n not equal to 0. This is the ideal discrete time differentiator. Okay, for designing that what you call impulse response of the ideal filters. Now, so you have to remember this all Gibbs phenomena, where Gibbs phenomena we know that. So this particular phenomena, oscillatory behavior in the magnitude response of the casual FIR filter, obtained by truncating the impulse response coefficients of the ideal filter. Okay, so with this, where n is ready to substitute, and as can be seen, so as the length of the low pass filter is increases as per this graphical representation, So the number of ripples in both passband and stopband increases. Okay, with the corresponding decreases in the ripple width. Okay, height of the target ripples remain the same depending upon the length. So by using this graphical representation, how it is happened that as can be seen, the Gibbs phenomena. Okay, it follows that the length of the low pass filter is increases. The number of ripples in both passband and stopband also increases with the corresponding decreases in the ripple width. So based on this all constraints, so height of the largest ripples remains the same independent of the length. Similarly, oscillatory behavior observed in the magnitude, okay, a particular magnitude responses of the truncated version of the other types of ideal filter. Okay, this is the main concept how it is happened. Gibbs phenomena, and this Gibbs phenomena can be explained by what you call treating this truncation operation as an windowing operation, because of we are designing the digital filter like the FIR filter. So using the windowing techniques, we have to follow these Gibbs phenomena can be treating the truncation operation as an what you call windowing operation. Okay, like this, it is represented in terms of the mathematical expression St of n is equal to Sd of n into omega of n, W of n. So where in the frequency domain, where St of e power j omega equal to 1 by 2 pi integral minus pi 2 plus pi Sd e power j psi the pi e power j omega pi into d pi. Okay, like this, where St of e power j omega, psi e power j omega are the discrete time Fourier transforms of Ht of n and what you call W of n respectively. So this is another aspect for the windowing operations. Okay, so the same phenomena, if psi of e power j omega is a very narrow pulse generated at omega equal to 0, it is only for ideal cases, or ideally a delta function compared to the variation in the Sd of e power j omega. Okay, so then St of e power j omega will approximate Sd e power j omega very closely. Like this, we have to observe this all narrow pulse centered at omega equal to 0. Okay, the variation in the Sd of e power j omega. That Sd e power j omega will approximate Sd e power j omega very closely. So length, we have to observe that length is 2m plus 1 of W of n should be very large. Okay, on the other hand, length 2m plus 1 of St of n should be as, when compared to the previous length, so should be as smaller as possible to reduce computational complexity. So this is the main motto, that we are trying to reduce that complex computational complexities. Previous length is 2m plus 1 W of n. Here this case is the length that 2m plus 1 of St of n should be as small as possible to reduce computational complexity. So with this, coming to each and every windowing techniques, how it is involved with a particular phenomenon, how it is affected mathematically and theoretically. A rectangular window is used to achieve the simple truncation. This is the main significance. So, presence of the oscillatory behavior in St e power j omega is basically due to what you call Sd of n. It looks long and not absolutely summable, and hence filter is unstable. Okay, so rectangular window has an abrupt St e power j omega transitions to 0. Okay, so this oscillatory behavior can be observed by examining the discrete time Fourier transform, say r of e power j omega of HWR of n. With this rectangular window, okay, this rectangular window, if it is main lobe and side lobes, how it is reflected. So Main lobes are increases, side lobes are decreases, and so on. Try to verify that here R into e power j omega as a main lobe or centered at omega equal to 0. Okay, so with this, so main lobe psi r of e power j omega characterized by its width 4 pi by 2m plus 1 defined by first 0 crossings on both sides of the omega equal to 0. Okay, as m increases, okay, it is one happened. If it is m decreases, easily you can try to verify that how it is. Main lobes or side lobes are either increasing or decreasing. If it is both sides of the omega equal to 0 as m is increases, so width of the main lobe decreases as designed. So area under the each lobe remains constant while width of each lobe decreases with an increase in the capital M. Okay, so ripple in ST of e power j omega around the point of discontinuity. This is a major observation while you are using this all particular what do you call that this case, that rectangular window. Okay, within this, the rectangular window has an abrupt transitions to 0 outside the range minus capital M less than or equal to n less than or equal to m, which results in the Gibbs phenomena in ST of e power j omega. Gibbs phenomena can be reduced either using the window that tapers smoothly to 0 at each end. This is one aspect. So, or we can consider providing the smooth transition from the pass band to stop band in the magnitude response with this how it is affect that all ST e power j omega. So using the tapered window causes the height of the side lobes to diminish. Okay, so with this we can consider these are all what you call fixed window functions. Okay, so with the corresponding increases in the main lobe width resulting in the wider transition at the discontinuity. So where if you are using the hand window, that W of n is equal to 0.5 plus 0.5 cos of 2 pi n by 2 capital M plus 1. Here that in terms of the range, interval minus m less than or equal to small n less than or equal to capital M. It is related to the fixed window like a Hanning window. Now coming to the Hamming window. So W of n is equal to 0.54 plus 0.46 cos of 2 pi n 2m plus 1 minus m less than or equal to n less than or equal to capital M. Okay, this is the fixed windows, how it is using the tapered window. It causes the height of the side lobes to diminish, that where with the hand and Hamming window. Go on writing the piece of code using this all windows, how it is reflected, what you call side lobes of main lobes of it is corresponding increases in the main lobe width resulting in the wide transition if there may be discontinuity or continuity, we will observe. So with this Blockman, W of n is equal to 0.42 plus 0.5 cos of 2 pi n by 2m plus 1 plus 0.08 cos of 2 pi n by 2m plus 1, where that range is here also we have to consider how it is reflected with the fixed window is. So it increases the main lobe with the resulting in a wide transition at the discontinuity or not. Okay. Now coming to this all are plot of this magnitude of the discrete time Fourier transform of this windows for capital M is equal to 25 or below the 25, or maybe where normally that case is where M is equal to 6 or 5 and what do you call 12 and so on up to 25, how it is reflected. Here it is shown that 25 where M is equal to 25 are shown like this. It is a rectangular window from here where x-axis omega by pi and y-axis the gain decibels. So here it is the magnitude of this particular window. If M is increases or decreases, how it is reflected. Now come to the Hamming window. So with this, here also x-axis is omega by pi and y-axis is the gain of in terms of the decibels. Now the Hamming window. So here it is. What are the all side lobes or main lobes? How it is varies with this the magnitude of the discrete time Fourier transform of these windows for if m is equal to 25. Okay. So like this, the Hamming window also like this. How the main lobe and side lobes of if it is reflected. So similarly, that what you call Blackman window. Okay. So like this, where graphically it is available, the plot of the magnitude of the discrete time Fourier transform of this particular window, that capital M is either increase or decrease. Typically, it is available where capital M is equal to 25, are shown in this all from rectangular window to up to Blackman window. Now coming to this magnitude spectrum of each window characterized by a main lobe centered at the omega equal to 0, followed by a series of side lobes with decreasing amplitudes. Okay, as for this previous analysis, the graphical analysis, to interpret this using this magnitude spectrum of each window characterized by main lobe centered at omega equal to 0, is followed by the series of side lobes with decreasing amplitudes. Now, the parameters predicting the performance of the window in filter design are what you call that main lobe width, okay, and relative side lobes levels. Okay, right, to verify that all in terms of the main lobe width is increase or decrease, or relative the side lobes levels either maybe how it is mapped, how it is observed. Okay, so with this, the main lobe width is delta ml, gives the given by the distance between the zero crossings on both sides of the main lobes, where is observed by using that graphically, right, to verify that all main lobes on both sides of the main lobes. Okay, similarly, the relative side lobes ASL is given by the difference in decibels between the amplitudes of the largest side lobes and main lobes. So with this, how it is affected using this all fixed window functions, so the main lobe width and relative side lobe levels, how it is varies. Okay, so with this graphically, the distance between the locations of the maximum passband deviation and the minimum stopband value is approximately delta ml. Okay, so width of the transition band, okay, where delta omega equal to omega s minus omega p less than or equal to delta ml. This is the relative width of the transition band. Okay, the minimum stopband value is approximately the delta ml. The width of the transmission band is like this. Okay, so to ensure a fast transition from the passband to stopband, okay, so window should have a very small main lobe width, okay, and to reduce the passband and stopband ripple data. While we are using the fixed windows, so this type of observation we will observe practically. Yeah, the area under the side lobe should be very small. Okay, and with this, unfortunately, based on this, to reduce the passband and stopband ripple, the side lobe should be very small, or like this. So what happens? These two requirements are contradictory, but what you call with this, so we have to overcome these all particular cases. It is suitable in the case of rectangular window. So Han window and Hamming window, and with Blackman windows, and Kaiser and Gaussian and so on. But especially these cases of in the case of the rectangular Han and Hamming and Blackman windows, okay, the values of the ripple does not depend on the filter length or cutoff frequency omega c, and is essentially constant. Okay, so in addition, delta omega approximately c by capital M, where previously we have seen that capital M is how it is varies from that capital M is initially where 2 and 5, 7, and 15, and 25, and so on. How it is reflected. Okay, like this, the value of the ripple does not depends on the filter length or cutoff frequency omega c, and is essentially constant. In addition, where delta omega approximately c by m. Okay, so with where c is the constant for the most practical purpose. Now, rectangular window delta ml is equal to 4 pi by 2m plus 1. Okay, where ASL is equal to 13.3 decibel, where alpha S is stop band 20.9 decibel, delta omega equal to what you call 0.992 or maybe 0.925 by m. Okay, so with this Hanning window, delta ml is equal to 8 pi by 2m plus 1, and where ASL is equal to 31.5 decibel, alpha is equal to 43.9 decibel. Delta omega equal to 3.11 pi by m. Now coming to the Hamming window, delta ml is equal to 8 pi by 2m plus 1. Okay, so where here it is the ASL is equal to 42.7 decibel, and alpha S is equal to 54.5 decibels, and delta omega equal to 3.32 by pi by m. Okay, so like this, the Blackman window is observed like this: delta what you call delta ml with 12 pi by what you call by 2m plus 1. So what is your observation? By using these fixed windows from this rectangular and Hamming with the Blackman window. Okay, like this, a typical value is assigned that how it is based on performance levels. And this fixed window filter design steps. So once we know that all that fixed windows are available, okay, one is hand window, Hamming window, and what you call Blackman window, and so on. So using this all fixed window functions, filter design steps we have to follow. So one is set, and where omega c is equal to omega p plus omega s by 2. Okay. The second step is choose the window based on the specified alpha s, and third step is estimate m using what you call delta omega approximately c by m. Okay, so for filter design process, we have to follow these all particular steps 1, 2, 3, and FIR filter design example. And while you are using the fixed windows, without windows, that somewhat it is we know that all merits and demerits. Okay, so we have to overcome all demerits. We go for the fixed. We have to choose that all fixed window functions for designing FIR digital filter. Okay, say for example, low pass filter of the length is 51 and omega c is equal to 5 by 2. Okay, here this is the major observation. Low pass filter is designed using hand window. If that omega by pi 0 to 0.2, 0.4, 0.6, 0.8, and 1. So in terms of that all gain factor 0 to minus 100, minus 50, and 0. Like this low pass filter design using the hand window. Okay, so now coming to the low pass filter design using the Hamming window. So what are the major observation while you are using this all two low pass filter of the length 51 and omega c equal to pi by 2. Okay, like this low pass filter designed using the Blackman window. So how it is affected using the FIR filter design? The low pass filter of length is 51 and omega c is equal to pi by 2. This is the major variation. Okay. Now coming to this next example, an increase in the main loop width in the associated with an increase in the width of the transition band. This is another scenario, like a decrease in the side lobes amplitude results in an increase in the stop band attenuation. This is the one aspect. Okay. Now, these are up to this level. These all are fixed window functions. How it is reflected. What type of variations are available while designing the FIR filter design. Okay. Now coming to these adjustable window functions. Previously, we have done that fixed window functions. Now coming to adjustable window functions. So with this, okay. So we can consider Dolph-Savici window. Yeah, like mathematically it is available. W of n is equal to 1 by 2m plus 1 by psi plus 2 summation k equal to 1 to m tk beta cos into k by 2m plus 1 into cos of 2n kn by 2m plus 1. So go on using this m value. If it is m is equal to initially 2 or maximum, we have seen that previously that using the fixed window functions, that m value is 25. How it is varies, main lobe and side lobe effects. So here using this all Dolph-Savici window, with this minus m less than or equal to n less than or equal to m. Okay, so where this amplitude the side lobes by main lobe amplitude, where if it is beta equal to cos h of 1 by 2m into cos h inverse of 1 by, okay, like this. So Dolph-Savici window will be involved with the adjustable window function, how it is reflected. So with this, where TLR of x is equal to cos of L cos of minus 1 x by of cos h of L cos h inverse of x. Okay. So with this, mod x less than or equal to 1, mod greater than or equal to 1. Okay. So this is one. Dolph-Savici window can be designed with any specified relative side lobes level, while the main lobe width adjusted by the chosen length approximately. Because of we are using adjustable window functions. Okay. Filter order is estimated. Okay, maybe first order, second order, third order, or 11th or whatever it is. But adjustable window function is reflected with the filter order is estimated using where n is equal to 2.05 and so on. Okay, where delta omega is the normalized transition bandwidth. For example, low pass filter is this one. Okay, like this, we have to verify this adjustable window functions are reflected. Okay, so this is by using this all directly we are right to decide the factor with how it is affect with the adjustable window function and what you call fixed window functions are involved for designing FIR filter. Okay, FIR digital filter is right to design using both the adjustable window and fixed window. What the major outcome of this by using the window function, adjustable window and the fixed window function. Okay, practically we try to verify using this MATLAB or Python, try to verify that outcome is reached, that our design aspects are fulfilled or not. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.